Okay, good. All right. So we're going to start today's class. Let me make sure this is up and running first. Okay, looks like, okay, so it looks like I'm okay as far as YouTube is concerned. All right, so we're going to start with chapter 12 today. And as you can see, the topic for chapter 12 is chemical bonding. So bonding, when we're referring to a bond in chemistry, we're basically referring to a force of attraction that exists between two atoms or two ions. So that's basically the focus for this chapter. But before we actually get to the bonding topic itself, we're going to get into some other topics. And the first thing we're going to talk about here is what we call periodic trends in atomic properties. So what we'll be looking at is how the properties of elements vary as you go across a period of the periodic table or as you go down a group of the periodic table. And there are a couple of properties we'll be looking at in this section before we actually get to bonding. So as stated here, the properties that are displayed by the elements are the original basis for the periodic table's design. I think I recall telling you about the guy who came up with the first periodic table or the first version of the periodic table. His name is Mendeleev. I don't remember what his first name was, but he was the first person to actually observe that if you arrange the elements according to their atomic masses, then you'll find that their properties will vary. And then after so many elements, they tend to be a repeat in their properties. And what we're going to look at is how these properties vary with respect to the electron arrangement or the electron configuration of the atoms of the different elements in the periodic table. So as stated here, these trends allow us to use the periodic table to make certain prediction about their properties and also about their reactions. So basically, based on the relative positions of elements in the periodic table, we can tell something about the reactions that they will take, that they will undergo, and we can tell some other information, for example, atomic sizes and other properties such as ionization energies and so on. So firstly, we want to look at some broad categories of elements. And there are two, or I should say three categories of elements that we can look at. That's one way of categorizing the different elements in the periodic table. You have metals and you have nonmetals, and then there's a third minority category known as metalloids, but we'll look at that later on. So as far as metals are concerned, these are their chemical properties. In their reactions, they tend to lose electrons, and as a result, they form positive ions, all right? So that's, I would say, the main property that is displayed by metals. Nonmetals, on the other hand, they tend to gain electrons and form negative ions. So if you have a reaction that takes place between a metal and a nonmetal, then what usually happens is that you have the transfer from the metals electrons, which will basically be transferred to the nonmetal, and you end up with what is called an ionic compound, and we're going to talk more about that shortly. As far as physical properties are concerned, when it comes to metals, these are the physical properties that are normally associated with metals. They tend to be lustrous, and basically what that means is that metals tend to be shiny. They tend to be malleable, which basically means that they can be beaten into shapes. So you can use them to make, things like pots and pans and engineering parts and so on. Metals also tend to be good conductors of heat and also good conductors of electricity, all right? So these are the physical properties that are normally associated with metals. Nonmetals, on the other hand, tend to be non-lustrous. In other words, they tend to be dull in appearance, not shiny. They tend to be brittle if they are in the solid state, and they tend to be poor conductors of heat and electricity. Now, I must mention that there's one exception to the last 2 points we made here, and that is a form of carbon known as graphite. Let me write it down here. So graphite is a form of carbon which turns out, we'll just put carbon in parentheses here, which turns out to be a very good conductor of electricity, right? So it's pretty much the only nonmetal which can be described as such. All other nonmetals tend to be very poor conductors of electricity, all right? Okay, so that's basically a summary of the physical properties of metals versus nonmetals. As I said before, there's a third minority group of elements known as metalloids, and they're called metalloids because they have some properties in common with metals and others in common with nonmetals, all right? And these are the 7 metalloids that you'll find or identify in the periodic table, right? So if I take, for example, silicon, if you look at silicon, if you could actually see silicon, you'll see that it's shiny in appearance, right? So it has that particular feature in common with metals, but at the same time, it is not as good a conductor of electricity as metals. So therefore, it has that particular property in common with nonmetals. So that's just one example, and we could look at the others and we can tell how they straddle a fence, so to speak, between the properties of metals and the properties of nonmetals, all right? So if you look at any periodic table and you identify the metals and nonmetals and metalloids in the periodic table, then you'll see something like this. Now, according to the key right here, the metals are in the green colored boxes, the nonmetals are in the purple colored boxes, and the metalloids are in the, I think this is, I don't know, orange colored boxes, right? So based on the different categories of elements that we just talked about here, you can see that the majority of the elements in the periodic table are metals, right? And they tend to be found to the left of the periodic table. And then the nonmetals, which are not as many, tend to be found on the right side of the periodic table, all right? And of course, the metalloids will be somewhere in between. Now, most periodic tables will have this kind of dark line here, which basically represents the line of demarcation between metals and nonmetals, right? So the metals are to the left of that line, the nonmetals are to the right, and then you have the metalloids, which would be immediately on one side or the other of that line, all right? So that's basically the periodic table in a nutshell with respect to metals, nonmetals, and metalloids. Okay, so as promised, we're going to look at how certain properties vary as you go across a period and down a group. And the first property that we're going to look at is the atomic radius. Now, the atomic radius is basically the distance between the valence electron, which is the electron on the outermost shell, and the nucleus of the atom, all right? I mean, it's actually more complicated than that, but we're going to go with that definition for now, all right? So if we operate on that basis, that definition, then there are certain trends that we'll see as you go down a group and across a period. Now, what you're looking at here is basically a representation of the different elements in terms of their atomic sizes, right? And based on what we observe here, we notice that going down a group, what you'll find is that the atomic size increases, right? And that is true for every group without exception, right? So for example, if you take group 1A, you see that hydrogen atom is very small, and then the next element is lithium, and so on and so forth, all right? So that is true for group 1A, for group 2A, and all the other groups in the periodic table. And the reason that occurs is because as you go from one element to the next down a group, what you'll find is that the valence electrons would be further and further away from the nucleus. In fact, if we were to use the Bohr model to represent the atom, let's say group 1A here, then this would be for the hydrogen atom in terms of the electron in an orbit, right? And then in the case of lithium, the electron would be in the second shell, which would be further away from the nucleus. And then the valence electron in the case of sodium would be even further away, and so on and so forth until you get to cesium, right? So that explains why going down group 1A, the distance between the valence electron and the nucleus would increase, and therefore the atomic size increases as you go down a group. And as I said before, that is true for every group in the periodic table, all right? So that's as far as going down a group is concerned. Now let's look at what happens when you go across a period left to right. Again, using this diagram here, using the models that are used to represent the relative size of the atoms, you'll see that going from left to right of any period, the atomic size decreases, all right? So that is true, for example, in period 1, which consists of hydrogen and helium. And then when you start with period 2, it starts with lithium and it ends with neon, you see a similar trend, a decrease in the atomic size, and that is true for all the other periods in the periodic table. Now, why is that the case? Why is it that the atomic size decreases as you go across a period? Well, if you think about what's happening as you go from one element to the next across a period, there are two changes that are occurring simultaneously. One is that you're adding an electron to the same energy level or the same shell, right? The valence shell, right? So in the case of period 2, the electron is being added to the second shell, right? Going from one atom to the next. At the same time you're doing that, you're also adding a proton to the nucleus of the atom. So what's the consequence of that? Well, the consequence of that is that as you go from left to right of the period, let's say you're looking at period 2, as you're going from left to right of the period, because you're increasing the number of protons in the nucleus of each atom, what you're doing also is increasing the attractive force between the nucleus and the surrounding electrons, right? So basically, you're going from, in the case of lithium, 3 protons to 4 protons, and as a result, the 4 protons will have a greater attraction for the surrounding electrons, pulling them closer to the nucleus, and that trend continues as you go from beryllium to boron, then to carbon, then to nitrogen, all the way to neon, right? And therefore, that explains why, as you go from one element to the next, the size of the atom decreases, because you're increasing the nuclear charge while adding an electron to the same energy level as you go from one element to the next across a period, all right? So that's basically how we explain the trend of a decreasing atomic size as you go from left to right of a period. Okay, any questions so far about the trends in atomic sizes? Any questions so far? Okay, so let's, okay, so this is just basically saying what I said before. This increased the positive nuclear charge and therefore pull the electrons closer to the nucleus. Okay, the next trend we're going to talk about here is that of ionization energy. First, we need to define what we mean by this term ionization energy, which is the energy required to move an electron from a gaseous atom. All right, so in other words, if you have a gaseous atom, X, right? Then, oops, I'm sorry about that, X in the gaseous state, then to remove that electron to form the positive ion, plus electron, the energy needed for this is called the ionization energy, all right? And what we're going to look at in this section is how the ionization energy varies as you go down the group and across a period, all right? So that's what the definition of the ionization energy is. All right, so, oh, here's an example here. I didn't realize that this example is here, so let me erase what I just wrote here. So in this case here, we're looking at the formation of the sodium ion from the sodium atom in the gaseous state. And in this case here, the ionization energy is the energy needed in order to form the sodium ion from the sodium atom in a gaseous state, all right? So that's what we mean by the term ionization energy. Okay, so because atoms can have more than one electron, then at least in theory and also in practice, you can have more than one ionization energy. So we can have what is called the first ionization energy, which, as you can see on the screen, is the energy needed to remove the first electron from the atom, such as in the case of helium, right? Now, helium has 2 electrons, right? So therefore, the first ionization energy is the energy needed to remove this 1 electron here, and you form the helium plus ion. And then you can have the second ionization energy, which is the energy needed to remove the second electron, which in the case of the helium ion that you're starting off with a +1 charge, when the second ionization energy is added to it, then you're going to end up with a helium 2+ ion here, all right? So basically, whatever the number of electrons that you have in an atom, then each electron can be removed and a certain amount of energy is required to remove each electron, right? Now, focusing on the helium example here, you'll see that in the case of the first ionization energy, this is the amount of energy for that quantity. And then for the removal of the second electron, you see that the amount of energy needed here is greater. Now, why is that so? Why is it that more energy is needed to remove the second electron than needed to remove the first electron? Well, the answer is simply this. In order for you to remove the first electron, what you're doing is removing an electron from an atom which is neutral, right? Now remember, the electron is negatively charged, right? So you're removing a negatively charged particle from something which has no charge. However, when you get to this stage here where you're trying to remove the second electron, in this case here, you're trying to remove a negatively charged particle from an ion which is positively charged, right? And you know that like charges, or I should say unlike charges, are attracted to each other. So therefore, it's more difficult to remove the second electron because you're removing it from something which is positively charged. And therefore, more energy is needed to carry that out. So therefore, that's the reason why the amount of energy needed here to remove the second electron is more than 2 times the amount of energy needed to remove the first electron in the case of the helium atom. And we see that trend basically in every atom. And this chart is showing you the ionization energies for selected elements, showing you the amount of energy needed to remove the first, second, third, fourth, and fifth electrons where applicable. So for example, if you look at, let's say, lithium, right? Now, you'll notice, I just want to show you this trend here. The amount of energy needed to remove the first electron is 520 kilojoules per mole. And then the amount of energy needed to remove the second electron is 7,297 kilojoules per mole. And then the amount of energy needed to remove the third electron is 11,810 kilojoules per mole, right? So you can see, based on the trend here for the removal of each electron, the first, second, and third, going from the first to the second, there's a big leap in terms of the amount of energy needed, right? 520 is the amount of energy needed to remove the first electron. And then there's a big leap to 7,297 kilojoules. Let me see what factor that is. 7,297 divided by 520. So that's like 14 times the amount of energy needed to remove the second electron than to remove the first electron, all right? And then from the second to the third, there's not that big of a gap between these two, all right? So how do we explain that? Well, if we look at the electronic configuration of lithium, let me go to my pen. The electronic configuration of lithium is 1s2, 2s1, right? So therefore, we have 1 electron in the first shell and 2 electrons in the second shell, right? So basically, it is much easier to remove this first electron here from the second shell because it is further away from the nucleus. Further away from the nucleus, all right? So it is relatively easier to remove this electron. Now, for the next electron to be removed here, it's more difficult. Why? Because these electrons are closer to the nucleus. Whoops, nucleus, all right? So that explains why there's this big gap or big difference between the 520 here and the 7,297 for the removal of the second electron. The first electron is further away from the nucleus and therefore much easier to remove because it's in the valence shell. And then when you get to the second shell, the second electron is harder, much harder to remove because it is closer to the nucleus. And then when you get to the third shell, it's a bit harder to remove, not as difficult, but it's a bit harder to remove the third electron, because after removing the second one, the nucleus will have a greater attraction for the electron that remains, and therefore the amount of energy needed to remove the second electron, or I should say the third electron, is higher compared to the ionization energy for the second electron. So if you understood what I just described here, then you should be able to explain the trends in terms of the removal of electrons and the amount of energy required in all of these atoms here, all right? Okay, so let's talk about now, let's talk about trends across a period and down a group, right? Now, this diagram that you're looking at here is a graph which plots the ionization energy, the first ionization energy, versus the elements in a particular period, all right? So the green line here represents that plot for period 1. The blue line is for period 2. In fact, I think I have the numbers here. Yes, the blue line here is for period 2. The black line here is for period 3. And the pink line here is for period 4, all right? And what do we notice here? We notice that as you go from left to right of any period, there is a general increase in the ionization energy of the atoms of the period, of the respective periods. So for example, if you look at period 1, which consists of hydrogen and helium, you see clearly that helium has a higher first ionization energy compared to hydrogen. Now, in the case of period 2, which starts with lithium and ends with neon, you see that there's a general increase. Now, there are 2 points where there's a slight decrease. For example, going from beryllium to boron, and then going from nitrogen to oxygen, all right? But apart from that, there is pretty much a general increase in ionization energy as you go from left to right. Now, I will not explain why you have this slight decrease going from from beryllium to boron, and then from nitrogen to oxygen. But that will be covered in general chemistry too. That's a bit beyond the scope of our discussion at this level, all right? But just suffice to say, generally across a period, there would be an increase in the ionization energy as you go from left to right of any period. Now, why do we observe this? Why do we observe a general increase in ionization energy as you go across a period? Well, the reason why is related to what we said earlier when we were talking about the atomic sizes. Remember, we said that as you go from left to right of a period, the distance between the valence electrons and the nucleus decreases. And that's because the nucleus, which has an increasing positive charge going from left to right, will have a greater attractive force on the valence electrons, all right? So what that means is that in order for you to remove those electrons, more energy is needed as you go from left to right of a period, all right? And that's the reason why the ionization energy increases. So just to summarize what I just said, let me scribble something. Let me scribble something here. So basically going from left to right of a period, so let me say from left to right of a period, one, atomic size. No, let me not start with atomic size. Let me say that one, the nuclear charge increases. The nuclear charge increases, and therefore, two, the force of attraction on the valence electrons increases. And three, therefore, the ionization energy increases. All right? So that's basically a summary of the explanation as to why, as you go from left to right of any period, the ionization energy increases. That's because as you go from left to right, a proton is added to the nucleus charge increases. That increases the attraction between the nucleus and the valence electrons, making the valence electrons harder to remove, and therefore more energy is needed to remove that electron, and therefore the ionization energy increases, all right? So that explains that particular trend in the periodic table as far as the ionization energy is concerned across a period. Now, the next thing we're going to look at is what happens as you go down a group. Well, as you go down the group, what you'll find, and this is true pretty much for all the groups, what you'll find is that the ionization energy increases, all right? The ionization energy increases. I'm sorry, I misspoke. The ionization energy will decrease as you go down a group, okay? So please make a note of that. The ionization energy decreases as you go down a group. Now, why does that happen? Well, again, it's related to the distance between the valence electrons and the nucleus, right? Now, in this case, as you go down the group, and we talked about this already, as you go down the group, the valence electron, the distance between the valence electron and the nucleus will increase. And what that means, therefore, is that the nucleus will have a decreasing attraction for the valence electrons, and therefore those electrons becomes easier to remove and therefore require less energy, all right? And that's the reason why. So let me get out of this here because I don't have any space to scribble anything. Let me go to my writing pad here and write down what I just said. So let me do this. So how should I write this? One, as you go down the group or down any group, atomic size increases, which means that two, the distance between the nucleus, distance between the nucleus and valence electrons increases. And then three, the attractive force becomes weaker. The attractive force becomes weaker as you go down the group, which means that for the valence electrons become easier to remove. And that's the reason why the ionization energy decreases as you go down the group. So just to recap this part, as you go down the group, the atomic size increases, which means that the distance between the nucleus and the surrounding valence electrons will increase. As a result of that, the attractive force between the valence electrons and the nucleus will decrease, which makes it easier for these electrons to be removed, and therefore less energy will be required to remove those electrons. So that explains the decrease in ionization energy as you go down any group. Okay, any questions about ionization energy trends going across a period and down a group? Any questions? Any questions? Okay, so one more thing I want to say here. So we talked about earlier the difference between metals and non-metals, and another difference is shown here in this particular graph. What you'll find is that metals, they tend to have lower ionization energies compared to non-metals, or conversely, non-metals tend to have higher ionization energy compared to metals. as a result, and this is related to what we said earlier concerning metals. Remember we said earlier that metals tend to lose electrons and non-metals tend to gain electrons. Well, the reason why metals tend to lose electrons is simply because they tend to have low ionization energies, right? It's relatively easy for the metals to simply lose electrons to form ions, all right? So that explains that particular observation concerning the properties of metals. Okay, so let's talk about a way of representing atoms. We call these Lewis structures, all right? And Lewis structures are very useful if you're only concerned with the number of valence electrons of a particular atom, all right? So that's what Lewis structure is all about. It's a representation that shows the valence electrons for the atom. So in a situation where that's all you're concerned with, then the Lewis structure or the Lewis symbol is very useful for that purpose when it comes to representing atoms. So for example, sodium has this electronic configuration, and as you can see, there's one electron in the outermost shell, right? So therefore we know that sodium has one valence electron. On the other hand, in the case of fluorine, this is the electronic configuration here for fluorine, and you'll notice that fluorine has a total of 5 plus 2 electrons in the outermost or valence shell of the atom. So therefore we can say and come to the conclusion that fluorine has 7 valence electrons. All right, so what's a Lewis structure? Well, basically it's very simple actually. We write down the symbol for the element and then we surround it with dots, and each dot represents a valence electron, right? So we use dots to represent the valence electron. So the example here is shown of boron, right? Boron has a symbol B, and if you look at the electronic structure of boron, in fact, let me write it down here. The electronic configuration of boron is 1s2, 2s2, 2p1, right? Boron has an atomic number 5, and therefore that would be the electronic configuration of boron. So in the case of boron, the Lewis symbol is going to be this right here, right? Each dot represents an electron, right? So therefore this is the Lewis symbol of boron. And let me just say that it doesn't really matter where you place the dots. You could have placed this dot here, this dot down here. It doesn't matter. As long as you have a total of 3 dots in the case of boron, then that would represent the Lewis structure of boron. Okay, so it's a very simple representation. And of course, the dots represents the total number of valence electrons, which are shown here, which I had up here as well. All right. Now, the point is being made that the electrons should be paired. But to be perfectly honest, that is not absolutely necessary, because I've seen in some textbooks where they don't have the electrons paired. But the point they're getting at here is that they're showing you that the electrons are paired here because you actually have 2 electrons being paired in the S sublevel for the second shell. All right. But I will not penalize you myself if you don't pair up the electrons in the Lewis symbol, all right? Because it doesn't really make a difference. Okay, and this is just showing you the unpaired electron, which is located in the 2p sublevel. Okay, so, and this is just showing you that you have the symbol of the element, which is surrounded by the dots. So here's another example, sulfur. If you look at the electronic configuration of sulfur, let me write it down up here. Sulfur has 16 electrons, so therefore, whoops, what did I do? So the electronic configuration of sulfur is 1s2, 2s2, 2p6, 3s2, 3p4. Whoops, that's 4. So that would be the electronic configuration of sulfur, which means that in the third shell right here, we have a total of 6 electrons. So the Lewis symbol of sulfur would simply be this. All right, the sulfur symbol with 6 dots surrounding it. And again, it doesn't really matter how you arrange the dots, as long as you have a total of 6 dots around the symbol for the element, then that would be the Lewis symbol. All right. Okay. Now, this is not correct because sulfur has 6 electrons in the third shell. So I just realized that this is not correct. This should be 3s2, 3p4, like I have here, right? So please make a note of that. This should be 3s2, 3p4, not 2s2, 2p4. Okay. So based on what we have just covered, we can basically see some patterns in terms of the arrangement of the elements in the periodic table as it relates to the Lewis symbols, right? And what you'll find is that at least for the representative elements, the number of dots will be equal to the group number, right? Which we talked about earlier in the previous chapter. So for example, for group 1A, you'll notice that the Lewis symbols have 1 dot for all the elements. For group 2A, 2 dots, 3A, 3 dots, and so on and so forth, all the way to the noble gases, which for each of these elements, they have 8 dots around them, with the exception of helium, of course, because in the case of helium, there are only 2 electrons, and those 2 electrons will go into the lowest energy level, which can only have a maximum of 2 electrons, all right? So that's a consequence of using Lewis symbols. You can correlate the number of dots to the group numbers for the representative elements. Okay, so let's talk about the formation of the ionic bond, right? You're going to learn in this chapter that there are 2 types of bonds. You have what is known as the ionic bond, and then you have the covalent bonds. Ionic bonds are basically formed as a result, as stated here, of the transfer of electrons from one atom to another. And we're going to talk about that in more detail in this section. Later on, we're going to learn about covalent bonds, which are formed as a result of electron sharing. And again, we're going to talk about that in more detail as well. Okay, so first thing I want to mention here when it comes to bond formation is that for the representative elements especially, but also for many other elements, they tend to behave in a way chemically that they try to end up with the same outer electron structure as one of the noble gases, right? So what that means is that in some cases, these elements will tend to either lose, gain, or share electrons in order to end up with the same electronic configuration as a noble gas element. So in the case of metals, they tend to form cations by the loss of electrons, and the nonmetals tend to form anions by the gain of electrons. In either case, they tend to form an electron configuration which correlates, or which is actually the same as that of their nearest group 8 element, all right? That arrangement usually consists of 2 s orbitals occupied by electrons and 6 p orbitals that are fully occupied by electrons in the outer shell of the atom, right? And as I said before, this is achieved by atoms either losing, gaining, or sharing electrons. Now, of course, that's the exception. The helium is the exception, as we said before, in group 8, because all other elements will have 8 electrons on their outer shell, all right? So these are the electronic configurations for the elements in group 8A. And as you can see, all of them have 8 electrons on their outer shell, with the exception of helium, which has only 2 electrons in its outer shell, all right? Okay, so let's talk about how ions are formed. Now, the example that I'm going to show you here is that of sodium. And sodium, if you look it up in the periodic table, has an atomic number of 11. So what that means is that the sodium atom will have 11 protons and 11 electrons. And this is the electronic configuration of the sodium atom. So the question now becomes, how many electrons would sodium lose in order to form the electron configuration of the nearest group 8 element? Well, if you look at the periodic table, you see that the nearest group 8 element is neon. And this is the electronic configuration of neon. So when you compare the electronic configuration of neon to that of sodium, you'll see that all sodium needs to do in order to achieve this electronic configuration is to lose that 1 electron in the 3s sublevel, right? And that's exactly what happens. The sodium atom will lose the 3s electron, and the result will be that you're now going to end up with an electron configuration which is the same as the electronic configuration of neon, all right? Another thing you'll notice is that now in this particular structure, the number of protons will be greater than the number of electrons by 1. In other words, this structure will now have an overall +1 charge. So that is basically the structure of the sodium ion. And as you can see here in the symbol of sodium ion, there's a plus charge being indicated here by the plus sign written as a superscript, all right? So that's basically how we explain the formation of the sodium ion from the sodium atom. That is formed as a result of the sodium atom losing an electron from the 3s orbital to form this structure, which has the same electronic structure as the nearest group 8 element, all right, which is neon. So that's what happens in the case of sodium, okay? Any questions about this? Any questions about the formation of sodium ion from the sodium atom? Any questions? Okay. So let's talk about the formation of a negative ion. And the example we're going to look at here is the chlorine atom. So if you look up chlorine, you'll see that chlorine has an atomic number of 17, which means that you have 17 protons in the nucleus and 17 electrons, right? And down here, you see the electronic configuration of chlorine. So the question I would ask myself in order to predict what kind of ion will be formed is what would be the group 8 element that is nearest to chlorine in the periodic table? So if you consult the periodic table, you'll see that the nearest group 8 element is argon. And if you compare the electronic configuration of argon to that of chlorine, you'll see that the only difference is that you have 5 electrons in a 3p sublevel, and here you have 6 electrons in the same level. So what that means is that the chlorine atom will gain 1 electron in the 3p sublevel, and the result would be the formation of the chloride ion. So the electron is transferred or attained by the chlorine atom, and you end up with the chloride ion being formed. And now we end up with a structure with the same electronic configuration as that of argon, all right? So that's basically what happens in the formation of a negatively charged ion known as an anion, all right? You have the transfer or the attainment of an electron by the chlorine atom to form the chloride ion, which has the same electronic structure as that of the nearest group 8 element to it, which is argon, all right? Okay, so that's what happens in the case of the formation of a negatively charged ion. So based on what we have just covered, we can explain the formation of the compound sodium chloride, because we talked about the formation of the sodium ion, and we also talked about the formation of the chloride ion. So basically, this is what happens. This is a sodium atom. This is a chlorine atom. The sodium atom, as we said before, will lose an electron, and the chlorine atom will gain an electron. So what is going to happen here is that the sodium atom will lose its valence electron and will enter the valence shell of the chlorine atom. The result will be the formation of the sodium ion, which has a +1 charge, and the chloride ion, which has a -1 charge. So therefore, you end up with a compound being formed between those two ions, which would be sodium chloride. And the ionic bond is basically the force of attraction that occurs between the positively charged sodium ion and the negatively charged chloride ion. So therefore, that attractive force is holding the sodium and chloride ions together, and that attractive force is called the ionic bond, all right? So that's basically what happens in the formation of sodium chloride. Now, this is just basically showing you the Lewis representation of the formation of sodium chloride. So here we have the Lewis symbol for sodium. Here we have the Lewis symbol for the chlorine atom, and you're going to have the transfer of electron from the sodium to the chlorine atom to form the chloride ion, all right? So this is the Lewis symbol for the chloride ion. That's the Lewis symbol for the sodium ion, all right? And as I said before, there will be an attractive force between the positively charged sodium and the negatively charged chloride to form sodium chloride. Okay, now if you understand that, then you should be able to understand the formation of this compound, magnesium chloride. Now in this case, things are a bit different because in the case of magnesium, the magnesium atom has 2 electrons on its outer shell. The atomic number is 12, so it has 12 protons and 12 electrons, but 2 of those 12 electrons will be on the outer shell. Chlorine, on the other hand, has 7 electrons on its outer shell. So what's going to happen is that the magnesium is going to lose the 2 electrons, but each chlorine atom can only have 1 electron, so therefore you're going to need 2 chlorine atoms for every 1 magnesium atom. So therefore you have 1 electron transferred to 1 chlorine atom from the magnesium. Another electron will be transferred from the other magnesium, from the magnesium atom to the other chlorine atom. And the result would be the formation of the chloride ion, 2 chloride ions actually. And therefore you have basically for 1 magnesium ion, 2 chloride ions, or you can simply write the formula as shown here, which is MgCl2, all right? So that's basically explaining the formation of magnesium chloride from magnesium and chlorine atoms, all right? Okay, any questions about this particular example? Any questions? Okay, so let's move on to a discussion. Oh, and by the way, same forces that we talked about in the case of sodium chloride is the same that's operating here in the case of magnesium chloride. The attractive force between the magnesium and the chloride ions will be the ionic bonds. Okay, now one important aspect of ionic compounds is the fact that they do not exist as discrete units as in the case of molecules. So as you can see here in this diagram here, the actual structure of magnesium chloride is basically a systematic arrangement of the sodium and chloride ions such that you can have what is called a repeat unit. A repeat unit is basically one part of the gross structure of the compound that repeats itself right throughout the structure of the compound. And that is true for every ionic compound, including sodium chloride. So there's no such thing as a molecule of sodium chloride. Sodium chloride does not exist as discrete units, for example, like water, which exists as molecules and represented by the formula H2O. So if you look at the structure shown here, what you'll find is that there's a 1-to-1 ratio between the sodium ions and the chloride ions, right? So for every sodium ion, there's a chloride ion. For every sodium ion, there's a chloride ion, and so on and so forth. Okay, so that's basically what happens in the case of any ionic compound. They exist as you can see here. Now, there might be a difference in terms of the pattern of the arrangement of the ions, but what they all have in common, ionic compounds, what they all have in common is basically a repeat unit, which is the same that repeats itself throughout the structure of the particular ionic compound, all right? Now, one aspect that is specific to the sodium chloride structure is that if you look at the structure carefully, you'll see that each sodium ion is surrounded by 6 chloride ions. So if you focus on this sodium ion right here, what you'll find is that there are 6 chloride ions surrounding it. So that's a sodium ion here, and then the chloride ions will be indicated by green circles here, 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 and here, right? So the sodium ion here is basically surrounded by 6 chloride ions. The term that we use to describe this, we say that the coordination number of sodium is 6, right? So that's what happens in the case of the sodium ion. And the same is true for the chloride ions, right? Now in this case, it's not as obvious, but let's say you focus on this chloride ion right here, then the 6 sodium ions would be that one, that one, that one, that one, and that one. And there's a 6th one, which is not obvious here, but if you imagine another unit cell over here, then this sodium ion, or I should say this chloride ion, will have a sodium ion above here, which would be the 6th ion surrounding the chloride ion, all right? So that's basically what happens in the case of the crystal structure of sodium chloride. Please note that the formula for sodium chloride does not indicate a molecule. That's a point I'm repeating. It's basically giving you the empirical formula where the ratio of the sodium to the chloride ions is 1:1, all right? So that's what happens in the case of sodium chloride. All right, so right through the structure, there's a 1:1 ratio between the sodium and the chloride ion, and therefore the formula that is used to represent sodium chloride is simply NaCl. Now, I want to say one thing about the relative sizes of the sodium and chloride ions, especially with respect to the atoms from which they're formed. What you're going to find is that if you compare the size of the sodium ion to the sodium atom, you'll see that the sodium ion is significantly smaller compared to the sodium atom. And what they did here is to show the diameter, or I should say the radius of the ion compared to the atom, which as a measure of the size. And as you can see here, the radius of the sodium atom is 0.186 nanometers, while the radius of the sodium ion is 0.095 nanometers. So basically the atom is about 2 times as large compared to the sodium ion. Now this begs the question, why is it that the sodium ion is small in size compared to the sodium atom? Well, the reason is that the sodium atom would have lost its outermost electron to form the sodium ion. So basically you're starting from a structure with 11 electrons in the sodium atom. When it loses 1 electron, you now have 10 electrons surrounding the nucleus of the sodium ion. Now, the nucleus does not change. The nucleus still has 11 protons before and after the removal of the electron. So what we're going to end up with in the case of the sodium ion is that the 11 protons will be attracting the 10 remaining electrons, and that force of attraction will be greater compared to what happens in the case of the atom, and therefore the electrons will be drawn closer to the nucleus, and as a result, the ionic size for sodium would be smaller compared to the atomic size of sodium. So that explains why the sodium ion is smaller compared to the sodium atom. Now, in the case of the chlorine versus the chloride ion, you'll see that the chloride ion is about twice the size of the chlorine atom. Again, question is, why is that the case? Why is it that the chloride ion is larger compared to the chlorine atom? Now, in this case, of course, to form the chloride ion from the chlorine atom, an electron would have to be added to the chlorine atom. So therefore, now the chloride ion will now have 18 electrons, but the number of protons will still be the same. So therefore, what will happen is that the attractive force between the nucleus and the surrounding electrons will be weaker, and therefore the electrons the electrons will be moving out further, and therefore the chlorine atom will be larger, or I should say the chloride ion, as a result, will be larger compared to the chlorine atom, all right? So that explains why the chloride ion is larger in size or radius compared to the chlorine atom. All right, so that explains those two trends. And what I just described is pretty much true for all elements when you compare the size of the atoms to the size of their corresponding ions, all right? Okay, some general statements here about metals. Metals usually have 1, 2, or 3 electrons in their outer shell, and therefore when the metal reacts, it tends to lose those electrons, all right, to form ions. And the ions, of course, will have a charge based on the number of electrons lost. So if it loses 1 electron, it forms a +1 charge. If it loses 2 electrons, it forms a +2 charge. And if it loses 3 electrons, then the charge on the resulting ion will be +3. In either case, the metal atom will end up with a noble gas configuration, all right? So that's what happens in the case of metals. And therefore, as a result, the ion will have a positive charge, right? And as I stated before, when we compare the sodium atom to the sodium ion, the positive ion, which is formed by the loss of electrons, will be much smaller compared to the atom from which it is formed, all right? So that is true not only for sodium, but also true for other metallic atoms. Okay, so in the case of nonmetals, they tend to have 5, 6, or 7 electrons in their outer shells, and therefore when they react, they tend to gain 1, 2, or 3 electrons so that they end up with a full outer shell, which corresponds to the electronic structure of the nearest noble gas configuration, all right? As a result, they will end up with a negative charge. So if the atom gains 1 electron, it ends up with a -1 charge. If it gains 2 electrons, then the charge will be -2. And if it gains 3 electrons, then the resulting ion charge will be -3. All right? And as stated here, the negative ion, and we saw this earlier, formed by the gain of electrons, will have a larger size compared to the non-metallic atom from which it is formed. All right, so this is just a table illustrating what we just talked about with respect to the atomic size and the ionic radius for different elements, metal and non-metals. And as you can see here, for all the metals that are located here and their atomic sizes are given, when you compare their sizes to the ionic sizes, you'll see that the ionic sizes are significantly smaller compared to the atomic sizes. So that is true for all the metals, all right? And then over here, we have the non-metals. And what do we notice? When you look at the atomic sizes compared to the ionic sizes, the ionic sizes are greater, right? That is true for all the non-metals, and we explained that. So that's basically a summary of what we just discussed. Okay, so how do we predict the formulas of ionic compounds? Well, it's very simple. Each atom, or I should say each ion, must have a noble gas electron configuration. And then based on the resulting charges of these ions, you can figure out what the formula for these ionic compounds are, all right? So as stated before, metals will lose electrons to attain a noble gas configuration, and nonmetals will gain electrons to do the same, all right? So just to use an example, let's look at barium and sulfur. When they combine, what would be the compound that is formed? Well, we can look at the electronic configuration of each of these elements. So this is the electronic configuration of beryllium, and this is, of course, the abbreviated version, and this is the abbreviated electron configuration of sulfur. As you can see here, in the case of barium, it has 2 electrons on the outer shell. In the case of sulfur, it has 6 electrons on its outer shell, right? So what's going to happen? The barium will lose these 2 electrons here on the outer shell and basically transfer them to the 3p sublevel of the sulfur atom, right? So the barium will lose the 2 electrons here, and it will form an ion which has the same electronic configuration as xenon. And in the case of sulfur, it will gain the 2 electrons that have been given up by the barium, and it will end up with the electronic configuration of argon, which is its nearest group 8 element. So therefore, this would be the reaction or the equation for the reaction, and this would be the formula for barium sulfide. So as you can see here, because the number of electrons lost and gained per atom is the same, the formula for barium sulfide is simply BAS, all right? And if you understand this, then you should be able to figure out the formula for pretty much any ionic compound based on the loss and gain of electrons of the atoms involved. Okay, one consequence of ionic bonding as a result of electrons being shared, lost and gained by atoms is that when you look at a group of elements, they tend to form compounds that has the same atomic ratio. So let me explain what we mean by that. If you look at, for example, the elements in group 1A, lithium, sodium, potassium, rubidium, and cesium, right? These are all the elements in group 1A. And if you look at, for example, the oxides that are formed, you see that there's a similarity in terms of the formulas, right? Basically, there's a 2-to-1 ratio between the group 1A metal element and the oxygen atom. So the formula for lithium oxide is Li2, the formula for sodium oxide is Na2O, for potassium oxide is K2O, and so on and so forth. If you look at the chlorides that are formed with these elements, you see that in each case, there's a 1-to-1 ratio between the group 1A metal and the chloride ion. Same is true for the bromide ions. And then in the case of sulfates, again, you see the same ratio between the group 1A metal and the corresponding, or the anion it's combined with, in this case, the sulfate ion. So in the case of lithium sulfate, it's Li2SO4. In the case of sodium sulfate, it's Na2SO4, and so on and so forth for the other elements. So that's basically a pattern that you would observe for group 1A. And you'll see similar patterns for the other groups as well. Okay, so this is basically the periodic table. And they're showing you specifically for each element, the outer shell or valence shell representation, or arrangement, I should say, for the different elements. And we see some patterns emerging. Elements in group 1A and 2A, well, they have their S orbital or subshell filled as you go from one element to the next in that section. So this is called the S block elements. Here we have the P block elements. Here we have the D block elements, all right? So this is just showing you the electron configuration of the outer shell or valence shell part of the atoms, all right? And as you can see here, the statement here, the group numbers for the representative elements are equal to the total number of electrons in the outermost shells of the atoms of the group. So just to give an example, I'm sorry. If you take, and I'm just going to choose an arbitrary example. If you take group 7A, you'll see that for each of these elements, there are 7 electrons in the outer shell. And the distribution is pretty much the same between the S and P sublevels for the outermost shell in each of these cases, all right? 2s2, 2p5, 3s2, 3p5 for chlorine, and you see a similar arrangement for bromine, iodine, and astatine, all right? So that's what is observed when it comes to the group numbers, the relationship between the group numbers and the valence shell electrons for each of the atoms, all right? Okay, this statement is saying that elements of a group have the same outermost valence electron configuration. Okay, so that's basically what I was saying in reference to group 7A. They have the same distribution of electrons between the S and P sublevel of the valence shell. Okay, so we talked about the fact that the atomic ratio between the alkali metal sodium and chlorine is 1:1 in sodium chloride. And the same is true for all the metal chlorides from group 1A, or the metal or the alkali metal group, right? 1:1, right? So these are the formulas for these elements combined with chlorine, I should say. LiCl, KCl, etc. All right, that's for group 1A, all right? And then even when it comes to nonmetals, you see a similar pattern. For example, in the case of group 5A, which contains nitrogen and other elements like phosphorus, what you'll find is that in terms of certain compounds, they have the same ratio. So when, for example, these elements are combined with hydrogen, you'll see this pattern here, right? The 1:3 ratio between the group 5 element and hydrogen, resulting in the formulas that you see right here. Okay, let me see what time it is. Okay, 5:03. All right, so that's basically a prediction that we can make with respect to the A group elements. They tend to, when they combine with a particular element for a particular group, they tend to have the same ratio between that particular atom from that group and the element that they're combined with. Okay, I think this is going to be the last thing we're going to talk about today. We're going to talk about covalent bonds, and we may not get into too much here. So I'm basically will be introducing this, and then we'll get into the fuller discussion next class. So as stated here, covalent bonds are formed as a result of sharing electrons between 2 atoms, all right? And what you'll find is that of all the chemical compounds that exist, the predominant bond that you'll find will be the covalent bond. So basically what this is saying is that most compounds are covalent in nature. So one aspect of covalent bonding that you'll find is that they result in the formation of molecules. And this is one big difference between covalent compounds and ionic compounds. As we said before, there are no such thing as an ionic molecule. Ionic compounds do not exist as discrete units. they basically exist as an ordered arrangement of ions, which is called a unit cell, or I should say, which is called a crystal structure. In the case of covalent compounds, they exist as discrete units. So for example, what you're looking at here is a representation of the molecule carbon dioxide, right? So basically, carbon dioxide exists as discrete units consisting of one carbon atom, which is combined with two oxygen atoms, all right? So as stated here, carbon dioxide bonds covalently as a result of sharing electrons and therefore exist as discrete units. Okay, so as stated here, the term molecule cannot be used in reference to ionic compounds because, as we said before, ionic compounds do not exist as discrete units, right? They exist as a large aggregate of positive and negatively charged ions that are ordered in such a way that you have repeat units throughout the whole structure of sodium chloride, all right? Okay, so let's talk about covalent bonding. Now, what you're looking at here is how a covalent bond is formed between two hydrogen atoms, right? So each hydrogen atom has a 1s orbital, which is singly occupied by an electron. So what happens is that when the molecule is being formed between these two atoms, they come into close proximity to each other and the orbitals overlap, right? And as a result, you're going to end up with a pair of electrons being shared between the two hydrogen atoms. And this basically constitutes a covalent bond because what happens is you're going to have an attraction between, you're going to have attraction, a strong attraction between the nuclei of the separate hydrogen atoms and the electrons that are shared between them. And it is that attraction which basically holds the molecule together. So therefore, that's why in nature, hydrogen exists as discrete units of two atoms in the molecule. And therefore, that's the reason why the formula for hydrogen is H2. So as stated here, in this particular arrangement, the electrons that are shared between the two atoms are most likely to be found between the two nuclei of the separate hydrogen atoms, all right? So basically, as stated before, the two nuclei will be attracted to the shared electrons, and therefore, that's what holds the atom, or I should say the molecule, together. We can also have the overlap between p orbitals, as you can see here, and this is what happens in the case of the chlorine atom. In the case of the chlorine atom, each chlorine atom has a single electron, which is located in a p orbital here and here, and therefore, when they overlap, they form a bond where those electrons are shared between the two atoms, all right? So that's what happens in the case of the chlorine molecule. Okay, let me skip all this here because I already described what is happening here. Okay, oh, and another thing too, which I didn't mention, is that in the case of the chlorine atom, each chlorine atom now ends up with 8 electrons on its outer shell. 2, 4, 6, 8 for this chlorine atom, 2, 4, 6, 8 for that chlorine atom. All right. Okay. So as stated here, the covalent bonding results with sharing of electrons. Now, if you have two identical atoms bonded to each other, then what will happen is that there will be an equal sharing of the electrons between the two atoms, right? So a good example of this is what we saw before in the case of hydrogen, right? And we see that also pretty much for all the diatomic molecules, right? If you remember, there are 7, or is it 8? 7 diatomic molecules that you should be familiar with: hydrogen, oxygen, nitrogen, then the 4 halogens: chlorine, bromine, iodine, and fluorine, all right? So in the case of hydrogen, we can represent it using Lewis symbols, where you have the 2 electrons here that are shared between the 2 hydrogen atoms, right? In the case of chlorine, this would be the Lewis symbol for the chlorine molecule. In the case of iodine, this would be the Lewis symbol in the case of iodine. And then finally, in the case of nitrogen, this would be the Lewis symbol. Now, what you'll notice is that in each of these cases, with the exception of hydrogen, the atoms themselves will have 8 electrons on their outermost valence shell, right? That is true in the case of chlorine. That is true in the case of iodine. And that is also true in the case of nitrogen, even though this looks weird, but these 6 electrons here being shared between the 2 nitrogen atoms can be counted towards the 8 electrons for each nitrogen atom. So for this nitrogen atom, you have 6 electrons here plus 2, 8, and the same thing occurs here. Now, another way of representing these structures is that we can use a line or a dash to represent a pair of electrons. So instead of writing the hydrogen Lewis symbol like this, we can simply write it like this, where this line here is understood to be the same as a pair of electrons, right? Similarly, we can write down the Lewis symbol for chlorine like this, the Lewis symbol for iodine like that, and finally the Lewis symbol for nitrogen like that. And in fact, there is yet a third way of representing these structures, which is the one I prefer, to be perfectly honest. So in the case of the chlorine molecule, we can represent it using this, Cl-Cl, and then we have 3 dashes there on that chlorine and 3 dashes here. Unfortunately, you can't see all of them. But basically, each of these dashes here represent this pair of electrons here. This dash here represents this pair of electrons here. And this dash here represents this pair of electrons here, all right? In the case of nitrogen, we can represent it like this. Dash here, dash here. So that would represent the Lewis symbol for nitrogen, all right? So as far as I'm concerned, you can use any one of these representations. I won't penalize you if you use one or the other, all right? They all represent basically the same idea. Okay, now this is where I think I'm going to stop. And then we're going to continue from here the next class. Now, as far as this chapter is concerned, you are, let me pull this down here, going to do the following assignments. Where is it? Let me go here. Then let me go here. And then let me scroll down to assignments. And, okay, so for chapter 12, let me publish chapter 12 here. And let me go into that folder. So for chapter 12, you will be doing, okay, you won't be able to do any of these quite yet because we have not done polarity. We have not done Lewis structures of molecules. We just started it, but we have not done everything we need to do for that one. And we have not done VSEPR theory. All right, so basically for now, you won't be doing any assignments for chapter 12. You won't be able to do any of these assignments until we complete chapter 12, all right? Okay, so that's basically, unless there are any questions, let me see here. Let me stop sharing. Okay, so are there any questions? Any questions concerning what we just discussed, or any questions dealing with any other issues related to this course? Okay, so if there are no questions, that's pretty much it. Oh, wait a minute. If we don't finish, if we didn't, yes, you can just email them to me. Yes, you can email your assignments if you can't upload them, all right? Any other questions in the remaining minute that we have left? Okay, let me see. I sent you assignment 20 by Canvas message because I cannot. Okay, no problem, no problem. If you email it to me, as long as it's a PDF document, I have no problem with that, all right? Okay, so if there are no, oh, you're welcome. Okay, so if there are no other questions, that's pretty much it for today. So I'll see you guys on Wednesday, all right? So until